So welcome everybody. I'm Maralikumar Venkat Subramaniam, short form Venkat, and welcome to the session, Introduction to Hive, with a case study on storing and querying Protobuf data in Hive. So this will be the agenda for today. I'll talk a little bit about Hive, not getting into the syntax or the statements inside Hive, but just give an introduction to Hive and what Hive can do, what Hive cannot do, and things like that. Limitations of Hive or features of Hive, however you can see it as, and a little bit into Hive, how data is stored in Hive. A little bit about protocol buffers and sequence files, UDF, UDTF, and SERDI. These are user-defined functions, and Serializer Deserializer on how to access data from Hive. And the last couple of items are how you customize Hive to store these protocol buffers and sequence files, how to set up tables for that protocol buffers and sequence files, and how to access data from there. And finally, there's no code and no demo for today. Yay. Okay. A little bit of introduction to Hive. Hive started at Facebook to handle their data growth. They used to use Python and MySQL and Oracle and regular ETL kind of tools to access to do their ETL stuff. For about a few tens of gigabytes of data, it was enough. But then they started getting terabytes of data, and regular ETL tools were not enough. So they started Hive for their internal processing. And then it eventually became an open source stuff, and it was taken over by Hadoop, Apache Hadoop, and now it's a widely used system. It's part of the Hadoop ecosystem, like HBase and many other software tools. The Hive is a very cost-effective way of processing very large amount of data. It can handle like hundreds of petabytes of data, and so you don't buy expensive servers to handle this. You just buy commodity hardware, but you buy thousands of them, and you start doing your Hive stuff, and it parallelizes massively and very easily and seamlessly. So internally, Hadoop uses a construct, a programming construct called MapReduce. So what MapReduce does, it takes one job, splits it into hundreds of smaller jobs, and collects the results in the end, and finally sends it to the client. So the advantage of using Hadoop and MapReduce is you don't have to do anything to get this MapReduce advantage. It's already there. You just write your code, and Hadoop infrastructure takes care of MapReduce stuff. So everything underneath is handled by the distributed file system called HDFS, which is a little bit different than your conventional Linux or Windows file system. It doesn't store data directly like how Windows or Linux does. It splits the files and stores it into different places, and there are multiple copies of data and all those stuff. And finally, Hive uses SQL-like language called HQL. It's not exactly SQL, but it's almost SQL. Most of the statements that work in SQL will work in Hive, but it's not ANSI compatible. So about MapReduce. So MapReduce it's not a very easy programming construct. It's a little bit involved. There is a big learning curve, even for Java programmers who have been doing this for a long time. So the advantage of using Hive is you write a SQL, and Hive will generate the MapReduce code underneath, and the user doesn't have to know about this, and the user will be happy not to know about this. So this is a big major advantage of moving from a regular MySQL or Oracle-based system into Hive. most of the code that you already wrote for Oracle and MySQL will already work in Hive. So people feel it's more suitable to move to a bigger data warehouse like what Facebook did. So what kind of applications does Hive work better in? It will be good for a large data warehouse, which is batch processed. That means you don't sit near a computer and just type a query and wait for the results. You let it run for a few hours or maybe overnight, and then come back, analyze what happened. So this kind of warehouse batch processed application is best suited for Hive, and it's best suited for relatively static data. If your data keeps changing every minute, it's very difficult to analyze it using Hive. So rapidly changing data is not Hive's strong point. So there are a few limitations or features of Hive. So Hive is not an RDBMS. There are no keys like primary keys and candidate keys and foreign keys and things like that. And you have to forget your normalizations. So Hive is this construct called write once and read many times. So you don't join on the fly, because you are talking about hundreds of terabytes of data for every query. So joining them every time during runtime is going to take a lot of time. So what we generally do, we denormalize it and create a table with a few hundred columns. Even if it is repetition, if the data is repeated, it's still fine, because the speed you gain in accessing a denormalized data is much better than normalizing it and joining it on the fly. And another problem or disadvantage of using Hive, there are no insert, update, deletes. So there are no operations. There are no statements like this. So once you have a table, it's not possible to say update this row where name equal to something. It's just not possible. And you cannot delete rows. So to do all these operations, you have to write MapReduce code or create a new table with SQL and removing those rows with SQL. So, but Hive doesn't by itself provide update, delete, insert statements. And the queries in Hive is going to be really slow. Most of them run, underneath it runs in Java, so there is high cost in starting JVM. One of the reasons why MapReduce is generally slow, even for a very small query, which takes a few milliseconds in Oracle or MySQL, is going to take like 20-25 seconds in Hive, because the startup cost is a lot. But things that are not possible to do in Hive, in Oracle MySQL, are possible to do it in Hive, because it can massively parallelize your large job into very smaller jobs. And Hive does not provide transactions. There is no concept of transactions in Hive. So it just runs one, or it fails completely. So it's not possible to use Hive for OLTP kind of applications. So mainly Hive will be used only for large data sets to mine information and to get insights into what happened. You go back a few days and you with your logs and see what users did, what users talked about, what users posted. Probably gain some insights about what users will do in the future, analytics kind of applications. So here are the components of Hive. This is coming from book Programming in Hive. So underneath everything is the Hadoop infrastructure itself, with the DFS, the HDFS file system, and the Hadoop infrastructure of name nodes and job trackers and task trackers and things like that. So name node is the only one which knows where your files are. And so there is a job tracker which, when you submit a job, it splits that job into very smaller jobs and assigns it to individual nodes. So inside individual nodes, there are task trackers which look into or monitor what each node is doing at that time, whether the task is running correctly or not. If it is wrong, then restart it or completely send a failure, things like that. And all the jobs go back to a job tracker, which finally sends the data back to the client. So that is the Hadoop infrastructure itself. On top of that sits Hive. So Hive consists of first a meta store, which is where details about tables, the fields, type of fields, the indexes, the partitions, and things like that. And then there is the driver itself, which given a SQL, it compiles, optimizes, and executes the code, generates MapReduce jobs, sends it to the Hadoop system, gets back the results, and all that kind of stuff. And then on top, and to access Hadoop, to access Hive, there are a few connectivity tools like JDBC, ODBC, command line interface, the Hive web interface, thrift servers, and things like that. So you use, and on top of that sits the UI tools like Hue, which is from Cloudera, and there is Karmasphere and Karmasphere, Qbol, and many others, which uses one of those connectivity tools to connect to Hive. Any questions so far? Okay, so how is data organized in Hive? So Hive is called schema on read. That means it doesn't matter what you put into Hive, it will just take it. So it doesn't check anything when you write something into Hive. So all the schema enforcement is done only while reading. So this is called schema on read. So you write one data and you can read it in many different ways. So if the schema and data doesn't match, you get mismatched data. So a few fields might be null, or there will be mismatched fields and things like that. But Hive will try to not fail the job because of this. It will just still send back junk results, but still most of the jobs will not fail. So out of the box, Hive supports TSVs and XMLs, JSON, GZIPs, and many other different file formats. So if you want to write your own file format, there are plugins and hooks given inside Hive, which help you dump whatever you want into Hive and read it in the way that makes sense to you. Now, what we did at our work was use the file format called protocol buffers. So this is the way our logs are organized into. So logs could be like regular TSV files or regular text files and things like that. But our logs are protocol buffer-based logs, which is a binary format. So this was developed by Google a few years ago for all their inter-process communications. So they were probably using some kind of a conventional tool like XML, JSON, I don't know. And they did not like whatever it was offering. So they they developed this one called a protocol buffer. And now they say almost all inter-process communications inside Google are done through protocol buffers. So what is a protocol buffer? It is a way of encoding structured data like a JSON or an XML, but the only difference is it's in the binary format. So it's not viewable by an editor like how we do with XML and JSON. Some see this as a disadvantage too, because it's not possible to see what's there in the file without using some tools to read into and see what data is inside this. But it's very efficient than XML and JSON. It's very extendable, and it's backward compatible. So you just create new fields and create new data, but still your old code will still work with your old data. The code compiled with older Java classes will still work with the old data. It's seamless integration. And it's about 3 to 10 times smaller. The file that you create in a protocol buffer is about 3 to 10 times smaller than a similar file that you would create with XML or a JSON. And it's 20 to 100 times faster. I don't know about these numbers, but this is what Google claims. It's about 20 to 100 times faster than XML. Another advantage of using protocol buffers, so when you have XML or a JSON, you create a file, but somebody else creates the XML parser tools for this, and there are tens or hundreds of parsers available. But with Protobufs, Google itself, they provide a compiler which will create classes, access methods, get set methods, build methods, serializing, deserializing methods, everything that's necessary to access this Protobufs. And it's from Google, so it must be good. Yes. And one more thing. So with this, it already generates Java classes, C++ classes, or Python classes. Everything is already supported. And there are like tens of other languages in which clients are supported, and people are already using like Perl and many other client tools, as, languages as clients to access these protobufs. So creating a protobuf is very simple. So you just create a structure like this. It's called a message, and put your fields in there, and then call this compiler called Proto-C compiler, and it can generate Java classes, Python, or C++ classes. And you just use that with your client, and it already provides you access methods and everything necessary to create a protobuf, read a protobuf, and everything. So I don't want to go into more details, and that's the link that has a tutorial and more information about protocol buffers. Any questions about protocol buffers? Yeah, so it can generate Java classes for you to access protobufs, but if there is a way for you to like use JNI or something for a C++ or Java, it will still work. So, but when you have a Java class, you can use only that to access the protobufs.
I guess my question is, if I use binary format for a particular data,
yeah, you can use any, yeah, to read that. Okay. Yeah, it's totally possible, yes.
So the binary format does not have any language?
No. Now, sequence files. Sequence files are another type of Hadoop file format, which is also binary, and it uses key value pairs of data. What is in a sequence file? So apart from this key value, there is also header information. This contains all the details that's necessary for it to read the key and the value. So it could have the type of the key, the size of the key, the compression codecs used for the key, and things like that. So this is one of the file formats that is internally used by MapReduce itself. So when MapReduce runs, it creates a lot of temporary files. So different maps creates its own outputs, and then somewhere it's all merged together. So this internal transfer, most of them is stored as a sequence file. The main advantage of using sequence file is that it's splittable. Now when I say splittable, So when, let's say you have a 256 meg file. Generally in Hadoop and HDFS, the block size is 128 megabytes. The reason is because when you go to a disk and read data, if you read small chunks like 2K, 3K, like how it's done conventionally, it's going to take a lot of read attempts to read terabytes of data. So for this reason, the block size of one read is 128 megabytes. So that the less time you go to a disk, the faster it will be. So in one read, you read 128 megabytes. So suppose you have 256 megabyte data, and you run a job on this. So it's given to one node. So the one node processes 256 megabytes. Let's say it takes 10 seconds for it to process, just hypothetically. Instead of that, if it is possible for it to read 128 megabytes 2 times in 2 different nodes. So instead of one node processing the whole file, 2 nodes processes half of the file each. So the whole job will be done in 5 seconds. So, but you have the system has to know where to split the file. So if you use a text file and if it doesn't know the record boundaries, and if it's split in the middle, it's going to be junk data. So this is the advantage of using sequence files, because there are markers in the middle of each block which tells you where to split the file exactly. So it's easy for the system to split one file into multiple files. All of them will be processed at the same time. Results will be combined together, and this will be very faster to access large data. So this is one main advantage of using a sequence file. And so it can also be compressed. So you can use any kind of compression algorithm. So for example, if you use a gzip, that's not a splittable format. But if your values are compressed using a gzip, each of the values is compressed separately, the file still becomes splittable. So you can use faster algorithms which are not splittable, but once it's used in a sequence file, it becomes splittable. And another advantage is it's like a zip. So you have thousands of smaller files. You can package all of them into one file and put that one file into HDFS instead of putting thousands of small 1K, 2K files. Because if you use smaller files in Hadoop, it's going to kill the name node very soon, because it is going to store details about each individual file. And instead of storing million files, if it has to store only one file, it's going to be really faster. And reading is also very quick. So instead of going and reading 2K for one file, if it reads 5 gig and 128 megabyte split, it's going to be really fast. So a little bit about how smaller files, how we did. Smaller files are processed into larger files. So we get smaller files like this. So we do some processing and package all these smaller files into one big sequence file. So all these 10K, 10K, 10K files become one 5 gig file, which is very faster efficient way of handling files inside Hadoop. So how individual files are organized? So we get zip files. So we retrieve the individual zip files from this zip, do processing, and write a key and a value. So this key will be any information that we want about these files, and then the value will be the file itself. And lot of these smaller files is packaged into one big sequence file. So here, this 5 gig file will be like this: key value, key value, key value, things like that. Any questions? Okay. SERDES. As I said, Hive supports many different formats out of the box, like TSVs, XML, JSON, zips, and many other formats. But It's also possible to store any kind of data, any format of data inside Hive, because it provides hooks for you to write your own processing code that will process the record format that only you understand. And this is called a SERD, short for Serializer Deserializer. So this helps you to store file formats, record formats that are not already supported by Hive. So SERD is an interface that lets you tell Hive how your data is organized. So whenever your table is accessed, Hive sends the request to your SERDs, and your SERDs processes these records and send the information to Hive. So SERD has two parts, serializer and deserializer. So deserializer is used when you do a select statement, for example. So when there is a select statement, Hive has to understand what fields to select, or where the data is and what fields it has to select, and what types these fields are. So when you do a select statement, the request is sent to a deserializer, your deserializer method. So inside a deserializer, it understands, it reads the chunk of data from HDFS. It doesn't matter what it is, but it reads this one chunk, which is a byte stream kind of data. And this deserializer transforms this into Java objects, which Hive can understand. Now Hive knows the field and the field type and the data of this table. So similarly, when you have to write back to HDFS, when Hive has to write back to HDFS, so when will this happen? This will happen when you do a statement like create table as select star from, or insert into select star from. If you use this kind of statements, then Hive has to read first and then serialize the data and write back into the new table. So this is where a serializer will help in. So serializer will take Java objects from Hive, from the first select statement. It serializes it and then creates bytes that can be written into HDFS. So that's a SERD. One more thing, so when I say Hive already supports TSV, XML, JSON out of the box, it means that there are SERDs written for TSV, XML, and JSON. Everything in Hive works as SERDs. So already existing SERDs are one of those examples. If it is already not there, you can write your SERDs. UDF, UDTF, and lateral view. So UDF is a user-defined function. So this is like a regular Oracle, MySQL stored procedures. So for every row of input, there is a row of output. So you can write your own UDFs and publish it in Hive and access them as function calls. UDTF is user-defined table generating functions. So here, for every row of input, there are multiple rows of output. For example, if you have an XML, which has a name and a phone number, and you have multiple phone numbers. So when you do a select name and phone number, it has to select name, phone number 1, name, phone number 2, name, phone number 3. So there is only one row of XML, but there are 4 rows of output. So that kind of UDF is called a UDTF, user-defined table generating function. So for Hive to understand how to make this transition, we call a construct called lateral view. So what lateral view does, so it takes the input, it takes the output of the UDTF, so which will be multiple rows for one single row, and then it joins that with the input row of Hive, which is the original input row, and then creates a table out of it so that Hive can output this as a rectangular table instead of one name and three phone numbers. Now we are getting into what we actually did. So we took, as I said, our log formats are in protocol buffer format. And since Hive doesn't understand protocol buffers by itself, we needed a SERD. Now, these protocol buffers are very small individual files, and we don't want them to be, we don't want millions of files inside our file system. So we packaged everything inside a sequence file. Now we have large sequence files which are individual protobufs inside. Now we need a SERDI to understand what is there inside. So there was this SERDI on GitHub by Edward Capriolo. This is where I started from. So I took this SERDI, which worked very well. But there were a few few changes that I needed to do. One problem is when Hive reads a sequence file, it only returns the value part of it. So we lose the key. So this SERDI had a provision for accessing both the key and a value, but it did not do the right thing. So I had to make changes for this. So basically, what it did was there was count. So basically, what you have to do, you have to read the file yourself, count how many records are there, what types of records are there, everything by yourself. So there were problems in there, and it did not read the keys. It only read the value, but the provisioning for key value was already there. So I took that and customized it so that it returns both key and a value. And one more thing, it did not support byte data, like binary data. Our logs had binary data in there. So I had to make changes so that it understands binary data as well. So the table setup for this. So as I had mentioned earlier, so to do protocol buffers, you need .proto files. So I created two .proto files, one for a key and another one for a value. So this key had multiple fields inside it, like name and phone number or serial number and things like that. So what is the advantage of using this key? So okay, I'll tell you the advantage later because I have to wind up fast. So what Hive can do, so to create a table, there are a couple of ways of doing it. You can, when in a create statement, you can give the field list right there. Or you can say, create this table, but read the field list from this Java class. So the SERDI will understand, so the SERDI will be called, and it calls the protocol buffer Java class that we created, which returns the field and field types. So Hive will be able to understand the field list from that SERDI. So it looks like the table is dynamic. So without this SERDI, you cannot do even describe table because it doesn't know what fields are there unless the SERDI is accessed. So you add a new field to that, update the SERDI, update the Java class. So when you run the describe again, you will automatically see the new field, but the data that you created with your old class will still work. So apparently the new fields will have nulls in the old data. So here is the create table statement for such a table. So if you see, it's totally different from an Oracle or a MySQL create table statement. So there are no field list here. So you just say create table name, and give the SERDI name in there. And then if you want to pass any properties for the SERDI, you pass properties in there. And then you write the input format. So input format is what tells Hive what kind of file is written in there. So here, so when you write a SERDI, one of the things that you have to do is to write a class for input format. So you pass that class name here. And then the output format is to tell Hive that is sequence file output format. Okay. Now, so with that SERDI, what happens if you create the table? You get two fields, key and a value. And all the fields inside a key, inside the .proto that you put in the key will be accessed as key.fieldName. And all the fields that you put in the .proto file with the value will be accessible as value.fieldName. So you can do queries like this: key, comma value from table name. So it returns the whole key as a list. Or you can say select key.field1, value.field1. So all these group by, order by, and everything. Regular SQL construct. So if you want to write a UDF, UDTF to access fields, so these are regular plain fields that are already available. But if you have to do something more to these fields, or if your fields are binary, for example, like ours, so you have to write a function which will understand this data. So for this, you write a UDF, UDTF kind of construct. So that is a syntax to write a UDF. So create temporary function, function name as the class name of your UDTF. So now this my function becomes a function call. So you can do this, my function and a field name from table. So if this were a UDTF, that is an example with a lateral view. So lateral view, it creates temporary table called T with the output of whatever my function outputs. So let's say it outputs two fields. So you access them as F1, F2 as an example, and then you can say T.F1, T.F2 from your select statement. So I'll just mention about this key field, why I use the key field. So in the Protobuf, there is a key and a value field in a sequence file. So now, if I don't say if I don't use the where clause, it has to do this my function for every single record. And if this is an expensive operation, then it has to open the Protobuf of every single record. But if you access it, if you use this where clause where key.field equal to something, it's going to open those Protobufs only when this is satisfied. So if you are accessing, for example, where some ID equal to something, instead of opening 10 million rows, it's going to open only the rows where ID equal to something, which is going to make your query really, really fast. So that's all I have now, and these are a few references that I took from, where you will find more information about whatever I talked about now. So, questions? Oh. That one?
Yeah, so the one that you modified, do you have that?
I don't know if I can publish that. I have to check with my work to see if I can publish. Yeah.
Is there a way that you could maybe like publish
Okay, I can do that. Yeah.
and what's your GitHub?
I don't have a GitHub. I'll create one and put it there. Yeah.
So Marali will be around.
Thank you, guys.